Hi, so I'll be discussing the overview of the digital signal processing systems or the DSP. So, as we have in the last two lectures, we have discussed the introduction on signals and introduction on systems. So, going for this digital signal processing system. So, first we have the three main questions regarding DSP. The first is, what is DSP? Now, when we go for what is DSP, here actually we mean that how do we need to understand the concept of digital signal processing? What is the relationship between this course and the other course on signals and systems courses? And next, we would discuss the uh, why we are going for this DSP or digital signal processing means what is the requirement of the DSP, what are the advantages and disadvantages of having everything processed in digital domain. Next, how to DSP or why do we need to do this digital signal processing, or how to implement the digital signal processing algorithms and other things. Next, here when we say this digital signal processing, main thing that we have a query, or anybody who knows the normal signals will have a query that everything is analog. I hear analog, I generate analog. So why do we need to do this digital signal processing? So whether it is any form of signal, that is audio, video, telemetry, radar, thermal, magnetic, ultrasonic sensor systems, or any digital device that we are having in our day-to-day life, the DSP involves in the manipulations of these signals, whether it is one dimension, two dimension, multi-dimension. I think you have gone through the signals and the systems that we discussed in the last two lectures. So here what we deal with in a normal DSP course is the Fourier domain representation, whether it to do Z transform and discrete Fourier transform. These are the two transform. One more Laplace transform is there, but we are avoiding it. Then how to deal with this discrete time signals and systems, the sampling and reconstruction of signals, then the systems, what is the system structure, what is the system analysis, and in terms of design of the filter as well as the filter structure. So we'll be dealing with this time to time. Next, going ahead, what we have is a little history. So to make things a bit cool, let's discuss a bit of history of the digital signal processing, or how this digital signal processing came into being. So first, if you go back to the ENIAC, which was way back in 1945, it was a true digital computer after this Charles Babbage's computer. Next, we have the miniaturization starting off from 48. You have studied in your microprocessor courses, these things. And then we have the silicon chip coming up in 58, followed by microprocessor by Intel in 71. And then we have the 80, 404, 80, 80, 85, 80, 86, and so on, 286, 386, 486, and so on. Intel Pentium series, 2, Pentium 2, 3, 4, and then the core series and other things. So we have the advance of silicon hardware going up daily, 45 nanometer, 32 nanometer, where earlier it was way back in this region in 48, 58, 71 was in micrometers. And now we have up to 10 nanometer, we have already reduced, and I don't know whether the 7 nanometer is already there in the market or not. So the advances of silicon and hardware are going on daily. Next, we have this age where we have deep learning, machine learning, AI, data science, which is coming up. And there also we need to process signal in the digital mode. So that's why your digital signal processing is very important. So before going to this, I'll be discussing the historical figures who have laid the foundations in this digital signal processing. Starting off is Fourier. He was headed in the 17th, 18th century. He was working. So without Fourier, we would not have DSP, because he showed us how to convert the time domain to frequency domain. So how to analyze signal via revealing the presence and magnitude of various spectral coefficients in the frequency domain, followed by how to process a signal by modifying its component, returning back to the original domain, and again transforming it back to the frequency domain, and so on. So in September 20, uh, this Luke Craig posted this particular uh, thing in way back in 2000, a very nice poem. One day, in a land far away, some mathematicians at play found a transform of a convenient form which is the basis of physics today. So the students of the physics background, I think, are aware of this. Next, convolving would wreck people's brain because convolving is very lengthy process if you do it manually. Still, the advent of Fourier domains for convolving in one means multiplication in the corresponding domain. So what we are doing here is that here we are, instead of doing convolution in the time domain, we are doing multiplication in the frequency domain. So just like we need to process analog signals in digital domain to make it easy, similarly, instead of dealing with in the digital time domain versions, we prefer to convert it back to frequency domain and then do multiplication and come back to the time domain. The next stanza is, got a trouble with an ODE, Fourier transforms will set you free. When once you would cry, now you just multiply by constant times the frequency. Now here ODE stands for ordinary differential equation, and Fourier transform will make it easier for you. Instead of solving the ordinary differential equation, you just have to multiply a constant times the frequency. To instead of solving a ordinary differential equation, you are just doing multiplication. Fourier transform backward and forth. I hope you now see their worth. For in every domain, advantages regain. Fourier was the salt of the earth. So nowadays Fourier transform become the salt of the earth because it is a very useful transform and totally used in all AI, machine learning, DSP and video signal processing, image processing. They are using it evenly. So just to make it a light-hearted, I am discussing this poem, which actually was by Glück way back in 2000. Now next is Simon Laplace. So he worked on the Laplace transform, which is the analog version of the Fourier transform. You can Fourier transform, you can say. So very useful for electrical systems, and these are the basis of the digital systems. So it is similar to Fourier transform, but it is more in general. So that's why it's analog. It is mainly used in the analog domain by the electrical engineers, and they are just like for electronics and computer guys. The Fourier transform is important. For electrical engineers, Laplace transform is more important, and it has more or less the similar relationship for them. So they are also having similar properties. They also transfer them into the frequency domain, and here we have the sine and cosine terms, which have both negative and positive exponential functions. So in DSP, Laplace transform may not be much use for analyzing, but for analyzing real analog filters, when you convert them from digital to analog or analog to digital, or fast Fourier transform, it is very important because based on the basis of the Laplace transform only, we are dealing with this. Next is Shannon. So based on his algorithm only, we are having the this capacity building of any bandwidth and other things. So any digital communication system is based on Shannon's work, and we have the bandwidth and channel capacity formulas given by them. And any person who is working on digital domain and with bits and bytes has to know his system, because even if you convert into bits and bytes, you have to know the bandwidth to transfer the information from one place to the other. So his was a pioneering research in the field of digital communication, and his Shannon sampling theorem will be used by us when we'll be converting the analog domain to digital domain, because without the Shannon sampling theorem and Nyquist criteria, we cannot deal with that. James Cooley and Tuckey. Cooley and Tuckey have designed a lot of filters. They were the ones before designing the filters came up with the fast Fourier transform to reduce the computation complexity or the weight on our processors. So the fast Fourier transform is the faster version of the Fourier transform, keeping the data same, but it reduces the computation more. So Fourier transform itself is a reducer, and fast Fourier transform is a reducer for Fourier transform. So both in the different ages are important, and present day all hardwares are having FFT based hardware. Any digital signal processing done in real time system or in your mobile processors are having the FFT hardware doing the work which was earlier requiring a lot of time, now in microseconds and nanoseconds, and the speed of the processor has gone high. So the fast analysis algorithms, wherever we are having the realization of radically new processing techniques, their algorithm of FFT is very important. So going ahead with the signal carries information and can be described as a function of independent variable in mathematics. So whether it is an analog signal, a digital image, or any one dimension or two dimensional dimension. So I have discussed the different signals in the last lecture, and the different systems we have discussed in the last lecture. Now going to signal processing, we need to represent the transformation and manipulation signals based on the information they contain. So the transform operations on signals may include transforming, filtering, introspection, spectrum analysis, modulation and coding, analog signal processing, digital signal processing. And the application areas include image, speech, biomedical, instrumentation, military consumer application. So we have a lot of applications for image processing, a lot of applications are there for speech, a lot of applications are there for biomedical, a lot of applications are there for instrumentation and control, a lot of applications are there for DSP. In military, we have many advanced applications, and in consumer applications in day-to-day life, our mobile phone, digital camera, internet, and anything, whether it is Alexa or a Siri, we are using all DSP systems. So coming to the basic concepts about the system, first, the system is having a device or technology for signal processing. All systems we deal with are actually analog, because say whatever I have here is analog, whatever I speak is analog. So systems with analog input and output are a must, whether it is your headphone or your mic, they are all analog devices. Then digital systems is the next stage, where we have memories and digital circuits which are dealing with the digital system. So for signals and systems that we have discussed, we have an input, we have an output, and we have a system. So that system may be a DSP, a FPGA, that is field programmable gate array, SOPC, system on chip, SoC, algorithm codes, anything. But we have everywhere a input, a output, and a block, which is called having system H. So the need for DSP where it is used is, say, it may be noise removal, enhancement of any signal or data, or say like modifying an image, old image with noise may be made more enhanced. Then we can put special effects, compression, decompression, reduction of data, encryption, decryption for security measures, feature analysis for detecting some patterns, feature extraction and recognition of some patterns. So mainly the three problems that we can have in any system is for input X, output Y and H. First, analysis, where we have X and H given to us and we need to find Y, means we have an input, we have a circuit. What is the output? So this kind of problems many of us have faced while doing circuit analysis. We know what is the input voltage, we know how the circuit is having how many resistance and uh, how many different capacitance are there and other things. And similarly, this kind of analysis we've done in network analysis, then calculating any output and so on. Next is the control part, where we have the system, we have the output. Now we want to find the input. Means, for example, I have a power plant where I know that the temperature is high, so and I know what is the system, and so but what I have to do is, for what input I can reduce the temperature. Say temperature is 43 degree is the output, but I need to have it at 33 degree. So I have to do something so that that 43 goes down to 33. So for that I need to know what input should I give to convert that 43 output to 33. So that is called control. The third is design or synthesis, where we have the input, we have the output. Now we want to design the system. Means what is the system for this input will generate that output. So these are the basic three problems. And here in DSP mainly we deal with the design part, where we have to design a filter which will give us our desired output. Say I have a signal X with noise and I need a output Y which will be noiseless. So I need to design a filter H which will remove the noise from the input X and give me Y. So DSP's common buzzwords that will be customed is A to D converter, means analog to digital converter. D to A converter means digital to analog converter, because we have to do both. Because when we are having, say you are having a microphone, you are generating analog, so you have to convert it to digital. And once you process the digital signal, you want to listen some MP3 songs. Those MP3 songs are in your hard drive or memory or somewhere in digital format. You have to convert it to analog and reach your speakers in analog format so that you can hear it. Sampling, quantization, aliasing, anti-aliasing, filters, algorithms, oversampling, these things will come to say uh, time to time, as we'll discuss in this course. We'll be discussing these things. So this is the sequence of event in any DSP chain event. Say we have a music signal or a speech signal, it goes to a microphone. This analog to digital conversion is done. Now it may be a real-time processing or it may be offline computer-based processing. So this digital to analog conversion will again be done, and the analog output will go to the loudspeaker, or this way or that way. So this is a normal DSP chain. So the process of processing any analog signal in digital methods is XA, which is the analog version, is sampled, quantized, coded to XN. So XN is the digital signal, XA is the analog signal. So anything I'm speaking here to the microphone is XAT. Once it goes into the computer, it is sampled, quantized, and coded in a data format, which is XN. The digital processing method is this XA converted to XN. Then we do the digital signal processing, and then we get output. So for input in digital, we get output in digital. But we are accustomed to output in analog. So we have to do a digital to analog converter and filter it and get a XA or YAT, which is the output signal. So if you compare analog signals with digital signals, is the analog domain is infinitely detailed. It is continuous in time, continuous in amplitude, whereas in digital domain we have discrete numbers, discrete in time and discrete in amplitude. So you have limits in time and amplitude, where we have infinite time and infinite amplitude in analog domain. So the challenge is a digital representation that adequately maps these analog values. And if every time it doesn't do adequate mapping, we will be losing some data. And data loss is not very helpful because we may lose information. So coming to the advantages of DSP, what advantages we have? First, high accuracy. Obviously, we can control the accuracy by choosing the word length, whether it is 8-bit, 16-bit, 32-bit, 64-bit. Next, high reliability. The VLSI, as very large scale integration of circuits have come up, we have ultra ULSI also nowadays, ultra large scale integration. So very big circuits are fabricated in chips, and it is repeatable, means we have any result that we get today, after many days also when we run the same program, we'll get the same result. Your program output, whatever is coming today, will not change tomorrow. So that is the high reliability. Then sensitivity to electrical noise is very less, and digital information can be encrypted for security purpose. This is the high reliability advantages of DSP. And flexible means DSP processor or software based or file programmable gate array or VHDL. All these can be programmed, so you can change the circuit or you can change the output pattern anytime, anywhere. Whereas if it is analog, you cannot directly change anything anytime. So anything that is compatible now may not be compatible later. Moreover, it is easy to integrate, and we can deal with high dimensionality of signals because nowadays we have abundance of memory. The cloud servers are there to help us. Obviously low cost, because nowadays digital costs improved, silicon costs have gone down, designing processors, reprogrammability, reconfigurability, digital storage is also come up cheap, because earlier we had a very big hard disk of say megabyte and kilobyte, and nowadays we have terabytes of memory coming in small chips. Price obviously will and reduce, and it has reduced time to market. Earlier the design was taking a lot of time, and due to this computer aided design facilities, it has reduced. So these are the various advantages. Along with this, data logging, data sciences have come up. Then adaptive capability, our systems can adapt time to time. We have machine learning and AI coming into the field of DSP and doing this adaptability. Now Every advantage has some disadvantages. So some disadvantages are sampling that causes loss of information because analog version is continuous and there is no loss of information. Once you convert to digital, you will be losing out some data. And analog to digital and digital to analog converter requires mixed signal hardware. Mixed signal hardware means one part is analog, one part is digital, or one part is digital and the second part is analog. And these are very complicated circuits. Then limited speed of processors. Nowadays, this is not a disadvantage, but still somebody will say that your processor is not as fast as mine. So we can put as a disadvantage quantization and round of errors. Other than the normal information loss, we have quantization loss also. I'll be discussing the quantization to noise ratio later on. So we can see at what rate we are doing this, and it is the whole thing is complex. So we have a thing, either we can increase the cost by increasing the speed, or we can reduce the cost but at the cost of reduced speed. So if you spend more, you get high speed processors. If you spend less, you get low speed processors. So the complexity you have to analyze whether your money is important or data is important. So this is the analog version, and we have analog signal processing, whereas in digital signal processing, we have the analog to digital and digital to analog converter. So these are the analog systems: acoustic domain, electrical domain. Again, acoustic, the whole thing is analog, and this is a digital domain. Then the programmer is converting them into numbers, and then these numbers are going back here. So in digital systems, these zeros and ones are coming, and D2A converter, and this is just to give you an emission feel. So just a case study of environmental system modeling. We can have current, voltage, frequency, temperature, humidity coming. We can do some signal conditioning. We have some analog switches, and then they are going to the CPU, PC, and we can do some signal processing here. So this part is electrical and non-electrical measurement. Here is analog and digital circuits, followed by the automatic test and measurement system. This is a SCADA, DTS, PLC, those systems are having this kind of things. MP3 player, you are well accustomed with that. So coming back, why digital? Flexibility, programmability, reproducibility, and precision. Advanced signal processing things that we can do: noise reduction, directional processing, feedback, frequency shaping, making the feedback cancellation makes it adaptive. Like a fan, say I'm recording this video lecture with the fan on, but the fan sound is muffled off because of the feedback cancellation. So we have digital signals which can be manipulated, or you can do digital. So we can do measurement, spectrum analysis, whereas frequency division, disturbance attenuation, these are the digital filter domain objectives that we can do. So we can have selective A to D converter, signal representation and sampling, manipulation, noise processing, and digital filters. So we have a lot of research objectives here. These are the multi-dimension DSP, is processing the relation of DSP systems, and so on. So the theory of DSP is sampling of analog signals, discrete time signal analysis, discrete time system analysis, fast Fourier transform, special algorithm for signal processing like filtering, then multi-rate signal processing using interpolation, decimation, and deconvolution and convolution. For implementation of DSP systems, we have general purpose processors, we can have microcontroller unit, we can have DSP chips, and we have different chips. TI or Texas Instruments is the leading market manufacturer. We have analog devices, Motorola, Lucent, NEC, which are generating hardware for DSP chips. So thank you. Till then, we will discuss these things in more details in the next lecture. Thank you.